here today, what I've kind of come to talk to you all about is Charmed HPC on OpenStack Sunbeam. And so, obviously, a bit of the title here, you can see that I dropped into, technical concepts, but, all right, let's see here. I'm trying to figure out how to move the page. Okay, there we go. So I'll just go ahead and give a bit of a short introduction here about who exactly I am. So first, a little bit about my background. I'm currently a high-performance computing engineer at Canonical. So my primary responsibilities are focused on actually leading the team now. So have a couple of engineers, and we're currently working on building an HPC product for Canonical. So a lot of my responsibility is focusing on the development work, but also kind of making sure that managing team resources correctly, and also kind of being able to coordinate everyone to actually contribute their part of the project. Outside of that, I'm also an Ubuntu member, so officially a part of the community. I like to organize events, obviously, given to why I'm here. So I've been pretty active in the Ubuntu Summit for the last 2 years. I'm one of the core organizers. I actually organized with Aaron and the rest of the community folks this UbuCon here. Outside of other community engagements, I also like to volunteer around various teams. So I am both a snap crafter, so kind of working with the open source community there, developing snaps. And then also, we have an HPC community that I kind of sort of lead, but basically we have a weekly call where we just get in, talk about HPC and all the fun things that we like doing on Ubuntu. And so one thing is, about working in HPC these days is that there's kind of a lot of criticisms that the industry is facing. And so the big thing is that obviously with the pace of innovation in AI, a lot of people are kind of starting to wonder, is high performance computing still relevant? Obviously finding that Moore's law is starting to become very non-economical in the sense that you can't just keep throwing money at supercomputers. Obviously you can buy bigger and better CPUs, but after a certain point, the cost just becomes so high that you start to really wonder, is it worth it? Another thing is also that Kubernetes has kind of taken over the world a bit here, where a lot of folks are starting to look at the traditional HPC batch scheduling systems and basically saying like, oh wow, that's boomerware. Nobody uses that anymore. Why do we need that? I want my auto scaling. I want my pods. I want my pod specs and all that. So obviously a lot of frustration. Where it's like, hey, I'm really into HPC. I love working on those technical challenges, and then kind of having people come in and be like, oh well, that's a dying industry. Kubernetes and AI is where it's at now. So why is HPC still relevant? And honestly, my response to that is negative feedback. Kind of sucks. It's obviously very important to be able to take negative criticism and kind of hear from folks about like, nah, you know what? I don't think your industry is really at the top of the game anymore, or it's kind of such a big relevant player in the pace of hardware innovation. And so, these gifts here kind of capture my reaction. When I kind of hear like, oh wow, why do you care about batch scheduling when Kubernetes is where it's at? It's like, no, it's still important. It's still something that's really useful, but obviously, if you're fully ingrained in Kubernetes world, you might not see it that way. But perhaps the detractors are telling the truth. So for example, one thing that you have to talk about and kind of have to point out about what's really happening in the market right now is a lot of following the money. So up here, I kind of have a lot of recent news articles that are kind of really highlighting, kind of the massive investments that are being made into AI infrastructure right now. Whether or not, it's going to pan out in the end, that might be up for debate. Whether it's going to kind of pop like crypto or if it's actually going to be revolutionary, we shall see. But not changing the fact that there still is a lot of money going into it right now. So for example, the Stargate project, building all those data centers, AI infrastructure companies are kind of really starting to pop off with investments and all that. Fluid Stack is becoming huge. A lot of companies are also building, giant clusters now. So for example, Tesla, built their, I think Colossus cluster, that might have been the name, but, very focused on AI. And then also the fact is that AI is just kind of having a very powerful effect on the HPC industry right now, where it's basically come in and basically told, hey, you're not going to get all these money to build these big traditional clusters anymore. And also starting to really think about, cluster architecture, where, you need to start supporting these more heterogeneous resources, where instead of having the biggest and best CPUs, you need to start thinking about also including like GPUs and MPUs and TPUs and all that. And so the other thing is too, is that Kubernetes is pretty easy to consume. I find that if I ask most people probably in this room to actually go ahead and set up a Kubernetes, most people would probably say, yes, I've used Kubernetes, and here's the tool that I've used. So I find with HPC, if I looked at Ken there and told him to deploy an HPC cluster, he might know what to do because he has a background in HPC or had a little bit of a background in HPC, but it's definitely been a while. And so what I'm kind of sharing up here is that Kubernetes is a very healthy and active ecosystem where there's a lot of new deployment tools coming out. So for example, you can kind of think of some of the really popular implementations like OpenShift or canonical Kubernetes, ways of basically making Kubernetes much easier for folks to use. Kubernetes is kind of hard to deploy by itself, but there's a lot of tools that just make it simpler. It's also a very healthy ecosystem of what's being provided by public clouds. So for example, you have AKS, you have EKS, you have Google's Kubernetes implementation, and then you also have a lot of local solutions as well for actually playing and learning Kubernetes. So you have like K0s, K9s, K3s, micro-K8s, all of those. And so it's extremely easy to use Kubernetes, maybe a bit difficult to set up and not hard to actually get started and start experimenting with Kubernetes. And however, when I think of Kubernetes, I think there's actually quite a bit of overlap between that ecosystem and the HPC ecosystem where, Kubernetes kind of has certain requirements, or folks that are looking to do AI on Kubernetes have a lot of the same requirements that you'll often find that folks who are using HPC systems are going to have. So for example, one big thing is always, resource allocation and scheduling. You might have Kubernetes, scheduling pods and spinning up new applications kind of based on demand. And then you also have like HPC systems that'll kind of allocate resources based on how they're requested. You need to have some kind of task management where if, multiple people are submitting multiple workloads, HPC is going to kind of have the same setup. And then you kind of then have some of the, basic bare bones things that any kind of distributed system is going to need to have, like identity and access management. You don't just want somebody showing up and having root access to your data. You're going to have service orchestration. Obviously, you want somebody to actually manage setting up your services, doing different things. You're going to need distributed storage. If my pod gets put over here, the data still needs to be available there if I'm still over here. You're also going to need kind of observability. Obviously, you're going to want to know the health of whether your job is running, you're going to want to know if your job is healthy, or if you're going to have kind of some kind of AI type workload, you're still going to want to be able to collect those metrics and actually analyze them. And then the other thing is that, if you're moving around a massive amount of data, you're also going to want to have high bandwidth networking. Unfortunately, 1 gigabit of Ethernet is not going to successfully exchange a multi-terabyte model, nor is it going to successfully exchange a multi-terabyte database or data set. And so now, the really important question to ask is, can we make HPC systems as easily consumable as Kubernetes? So, if I can go out here and I can say, oh, okay, basically sudo snap install K8s, and, within 3 commands you have a fully functional Kubernetes cluster, can we kind of do the same thing with HPC systems? Can we make HPC the experience of actually setting up and using an HPC system just as easy? And I think, well, yes, we can. And that's where it kind of comes back to the title here, where I think we can possibly achieve that using Charmed HPC and OpenStack. I think we can still kind of get a little bit closer to where, okay, maybe we won't have the 3-command install or setup right now, but we can still make it really easy to actually go ahead and start setting up an HPC system. So you might be wondering, actually, okay, this guy has said Charmed HPC, what actually is it? And in years prior, or presentations prior, I would throw a very, complex chart up here. And I would go through and spend 20 minutes kind of outlining every different piece of it and be like, well, if you follow the orange line to the storage, it goes ahead and does this on this thing right here. And then I'll say like, oh, but if you take the workload manager, it's going to interact with this bit right here. But obviously, I found it's kind of a bit technically dense and hard to follow, especially if somebody who isn't necessarily fully aware of like how an HPC system actually goes together, or also it's just kind of like, all right, this is like a really crazy chart that I'm just trying to understand, yet this guy is like speaking at like the speed of sound, trying to tell me how this actually works. And so I think a great way of saying it is I kind of look like Charlie Day from It's Always Sunny, trying to go through that, where it's like you have all these different interconnecting lines and you're just trying to actually explain how it goes together and how it works, which, I don't think is a very helpful way. So instead, I'm going to try a little bit different way of actually breaking down what Charmed HPC is. And so first, I'm going to introduce you to my good friend, Beowulf. And so while this here is the, I think, 2012 animated movie, retelling the epic of Beowulf, the Old English poem, Beowulf was also the name of the first HPC cluster that really popularized the Beowulf architecture, which kind of looked at having 4 core components. And so the first part there was the workload management aspect, where okay, you have a distributed system of commodity hardware that you need to make available to a group of users, but obviously you don't just want all those users hitting the cluster at the same time and beating it up. Instead, you want to kind of have some level of management there to actually control those resources. The next thing you're going to kind of want to have there is the identity and access management bits, where effectively, you want users to basically be able to say like, oh, I'm Johnny, I'm Ken, I'm Rajan, all that, and basically make sure that, okay, they can't overlap or touch data they're not supposed to have access to. You're also going to kind of have the distributed storage bit, or shared storage or parallel storage, depending on the implementation you're using. But the idea is that, okay, if you have all these distributed pieces of commodity hardware, obviously your data is going to need to be available on each individual set of those nodes. And so that's where the distributed storage comes in and actually making sure that's delivered. And the last thing, which is, I guess you could say kind of optional, but still highly recommended, is to have a high bandwidth network where you can quickly exchange large amount of data very fast. And so now, I guess you could say, we'll go into a little bit more of a in-depth view of what like an common HPC cluster architecture is, where effectively, okay, you have workstations where people are going to be logging into the system. Then you're going to have head nodes, which are basically kind of the jump hosts that folks use to actually go ahead and access those compute resources. Then the compute nodes are actually the hardware that's responsible for running the workloads. And then you're going to have the storage bits that are just kind of responsible for keeping the data there. So for example, you could say like, okay, you're going to have like the application data, so that's going to be user applications. And then you're going to kind of have this scratch base where users can write a lot of data very quickly, but then eventually it'll get cleaned out to free up more space for other people. And then the next thing you'll kind of look at is that you can kind of then start to bolt on some additional auxiliary services to basically improve your experience. So that's typically where identity management gets put, but I still think identity management is very important. And then you also get like things like observability and monitoring, where you're actually going to be able to get insights into the health of your cluster. And then the next thing here is then the network, where okay, the public net might be a little slower, but then where those kind of high-speed interconnects come in is more of the internal network that the nodes can use to communicate back and forth with each other. And so now, to kind of outline the overall how Charmed HPC comes together, we'll go ahead and kind of put together in steps here. So typically the way I like to think of it is that the workload manager is the core of the HPC system. So basically, it won't be able to function unless it actually has that workload manager there, kind of being able to take in user resource requests and actually kind of efficiently schedule those requests on the variety of nodes that you have available. And so the workload scheduler implementation we use within Charmed HPC is Slurm. And so if you're kind of wondering what Slurm is, it's basically an acronym, or it started out as an acronym for Simple Linux Utility Resource Manager, which if I can tell you anything about Slurm is that it is not a simple Linux utility resource manager. It is actually quite complex. It has over 250 configuration options, and yeah, it just turtles all the way down from there. So still, though, Slurm is also a very popular workload scheduler implementation. It's about on like 60% of the top 500 supercomputers. So a lot of people like using it. It's pretty much available on any major distribution. And so a lot of folks are going to go ahead and use it. And so here, we'll kind of go ahead and we'll actually start with Slurm as kind of the core of our Charmed HPC cluster. And then the next thing that we'll kind of then do is add a little bit of pizzazz to it, as indicated by the magic wand and sparkle. But basically what that is doing is actually adding kind of the auxiliary services that make Slurm even better. So kind of starting right here, you'll see MySQL. What MySQL is for is kind of storing that accounting data. So if you're basically interested to say like, hey, how much resources of the system are my users using, that information will actually get logged in MySQL, and then you can kind of build integrations against that to create like a billing system and all that to see who's using what. Then you can have like InfluxDB, which is a time series database for actually kind of tracking job performance. So if you're kind of finding like, hey, my jobs aren't performing so well, or are users potentially scheduling jobs that aren't as optimal as possible, you can use something like InfluxDB to actually get that data. And Then the next thing is that you actually have the specialized hardware resources. So typically those will go ahead and live on the compute nodes that are managed as part of Slurm. But I use the NVIDIA logo here, but you can also use like AMD stuff and all that. But the idea is that like, oh, you can actually set up the GPU drivers as well. So for example, if you want to schedule like an AI job on Charmed HPC, it'll go ahead and set up those drivers. The next thing is that you'll have InfiniBand, which is a popular high bandwidth networking implementation where you can get up to 800 gigabits per second. So a lot of data all at once, but very crucial for HPC setups. So yeah, you'll basically kind of have that pizzazz. So while in this slide, you'll kind of have the workload scheduler. Without all this additional stuff, you can't quite get the best possible performance out of your cluster. Then the next bit here is actually going ahead and adding the distributed storage. So for that, that will basically provide the storage for the user workloads. So for example, Slurm, using like distributed compute nodes, you want to make sure that your data is available everywhere where you need it to be. And so you can use possibly, say, a storage implementation like NFS or SafeFS to actually get that data there. So that's kind of the two current implementations that we support. There's also lots of popular HPC file systems out there like Lustre and GPFS and all that. But they're a little bit more fun to try and set up, so we're adding them currently. But those are options that you have available for those highly parallel workloads. Yes? So typically when I say NFS, I mean like normal NFS. I know that we do want to support PNFS, but I found that like at least for testing, NFS is a really good first choice. And then SafeFS, we have a lot of resources that we can leverage there because like I know a lot of Ceph developers, and so it just makes it a lot easier. But yeah, the idea is that as you kind of said with PNFS, the storage implementation can actually be modular. So as we kind of get requests to add support for like PNFS or Lustre and all that, it is modular in the sense that we can just basically write the code that actually makes it work, and then we can just plug it in. So we could take like SafeFS out and then replace it with something else. Yeah. Thank you for the question. So yeah, so we'll have the distributed storage here. And the next thing that we'll want is the identity management. So effectively what will happen is that this will live on a control plane. So basically going over that, the way we kind of architect Charmed HPC clusters is that we have both the compute plane, so that's typically machines so that we can get the best possible bare metal performance, and then we have the control plane, which is much more suited for running indefinite services, which Kubernetes is actually quite good for, kind of separate from those machine resources. And so with the identity and access management, usually HPC systems traditionally use LDAP. You can also use like Enter ID or Active Directory. But here we're using a newer LDAP implementation or LDAP server implementation called GLAuth, which is quite the nice thing about it is that it can be SQL backed. So if you don't like writing LDAP interchange files, which I don't, you can instead write SQL queries to actually create and manage users. And so we use those two services to basically actually manage and provide our users. And then the next thing here, which is very important, is to actually add the observability integration here. So obviously, you want to be able to assess like what's the overall health of Slurm, what's the health of MySQL, what's the health of my identity stack. So we'll actually go ahead and we'll add that observability implementation here. And what you're going to kind of see is that, okay, we already have like Loki, Prometheus, and Grafana, which is kind of the standard observability stack that you'll get with Kubernetes. But then you might be asking, how do we actually collect those metrics and then forward it back to Grafana? And so for that cute little robot guy there is effectively Grafana agent, and that's just basically a daemon that's running on our Slurm control node that's just basically gathering metrics from Slurm and actually pumping it back into Grafana, so then you can actually get alerts and you can visualize your metrics. So then after that, when you actually start to kind of look at user workloads, that's a little bit more, I wouldn't say the Wild West, but you can be a lot more flexible there with how you actually want to manage that. So in HPC, there is the popular package manager, SPAC. There's also Easy Build. And then you can also have like containerization runtimes like Aptainer, Singularity, Enroot, Saris to actually provide like user workload support there. So basically, TLDR of that, a lot of different ways to run user software. Basically, all you have to do is actually just make sure those tools are installed in the compute nodes. And so the last thing that you kind of need to like really actually kind of take into consideration here is like, how do the planes communicate back and forth? So for example, you have the control plane here, so that's in Kubernetes, and then you have the machines, and basically they have their own kind of isolated DNS. So in the sense that they can't really talk back and forth because they're kind of two separate clouds. And so basically what we have to do is go ahead and expose the control plane services to the machines so that they're actually able to communicate back and forth. And typically with that, we use this cute little gopher guy up here, traffic. And effectively what it'll do is it functions as a reverse proxy that'll go ahead and actually expose services like our LDAP server or our Grafana server to our machine cloud. And then at that point then, things like TripleSD can actually then bind against the LDAP server, and then Grafana agent can then actually forward metrics up to Grafana and actually reach it. So now the fun question is, does it actually all work? So if the internet favors me, which I hope it does, we'll try and play this video here. So what you're going to see here is we're just going to show you like a really small HPC cluster that's running on Azure here. So we have two partitions deployed, one with high bandwidth networking, and then another that actually has those GPU resources available. And then what we'll go here is we'll just kind of upload some really simple job scripts to our head node, which is basically our jump host for actually accessing the cluster. So go ahead, type out SEP, very rudimentary, groundbreaking UX for actually interfacing with the cluster. But we'll go ahead, we'll actually upload that. And then we'll SSH into the jump host there. And the next thing that we'll do is we'll actually then go change into our basically home directory that exists on the distributed storage. And then here, what we'll show is a job script that's going to go ahead and request 2 nodes of the high bandwidth network, and then run a simple MPI benchmark, which is message passing interface, on that partition to effectively test or benchmark and measure the performance of the InfiniBand cards that we have. So we'll go ahead and run that. Once again, very groundbreaking CLI there, or UX. We'll actually go ahead and we'll read the file, and then there, what we can kind of take away from this video is that we were able to achieve the advertised performance of those InfiniBand cards, which was about 200 gigabits per second. And so then the next thing that's going to happen here is we're actually going to go run a job that requests and uses the GPU partition that we have. So here it'll show basically our very simple request, basically say, hey, Slurm, go out and go get me a node that has a GPU. So we'll go ahead and we'll go submit that. Basically, what we're going to do is go run some very simple arithmetic operations on that GPU. So, maybe taking $1 million resource and, doing 1 + 1, but hey, we're going to prove it works. And then we'll go here, and you can kind of see it, the text is very small because, I wasn't expecting it to be this small, but the idea is that, hey, we were actually able to get the device info and then run those operations on the GPU. So yeah, now that I've kind of, run through what Charmed HPC is, you might be now sitting here and wondering, okay, so he said Charmed HPC on OpenStack Sunbeam. So what does OpenStack Sunbeam have to do anything with Charmed HPC? Well, I'll tell you why. That 2-minute video cost us $20 to make. HPC resources in the public clouds are very, very expensive. So here, looking at the 2 instance types that we actually requested on Azure, the first one that we requested, actually we requested 2 of them, the high bandwidth networking nodes. Those each cost about $2,600 a month, just for 1 instance. So you can imagine, $2,600 over a month, that's about, say, $4 an hour almost, just to use one of those nodes. And even to really actually benefit from high bandwidth networking, you need at least more than 1, so you actually have to pay for 2. And then actually then for the GPU instances, luckily they're a little bit cheaper since the public clouds want to sell GPUs to people. That was about $1,500 just to request one of those nodes. So you can kind of see like, okay, what we showed you in that video was like a really small cluster just to prove out the functionality, but to actually build something that's useful where you're actually training like LLMs, you can kind of see how that's going to get very expensive very quickly. And so the benefits that we kind of try to see with Charmed HPC is the ability to have portable HPC infrastructure, on public cloud. So for example, if you're, say, on Azure and you decide, oh, well, I don't want to pay for Azure's resources anymore, it should be really easy for you to just get quickly spun up on GCP. And kind of the same way for like AWS and Oracle. You should be able to kind of take your infrastructure where you want to go without necessarily being locked into a particular vendor. And we should also show that same love to private cloud implementations where, okay, sure, you might have a longer, cluster bring up time, but, you're also kind of having a little bit more predictable costs with your data center. So a couple of popular implementations, we have OpenStack, that's kind of more for like the enterprise deployments, the big clusters. We have Moz for if you want to be closer to the metal. And then we kind of have more of the training stuff like Canonical LXD, where, instead of like, hey, you're deploying a huge production cluster, instead you're kind of having something more of a learning environment where you can just kind of play around with the HPC system. So then you'll sit here and you'll say, okay, so why do you want to use OpenStack Sunbeam? Well, it's an extremely straightforward setup, at least for a single node. So you can kind of think like, okay, we're going to use the public cloud or this huge expensive data center, to run, jobs like weather modeling, CFD simulations. But, if you're just training somebody, you don't need to give them access to those $1 million resources. If you just want to teach them, okay, this is how you request a job, this is kind of how you're able to ping pong back and forth between two nodes, you can give them a much less expensive and virtualized environment. And so for that, you can use something like OpenStack Sunbeam, which is kind of a very easy way of actually like deploying, a full OpenStack system. So you'll kind of see here, basically to actually get a full cloud, on a single node working, all you have to do is run these 4 commands. So first, all you really just have to do is like a sudo snap install OpenStack, specify your channel. After that, you'll just have to prepare your machine for actually running OpenStack. After that, then you'll just do like a cluster bootstrap. If you don't need anything fancy, you can just accept the default options. And then after about 30 minutes of actually setting up all the different services that bring together OpenStack, then all you have to do is configure it to actually get your OpenRC file, which just basically contains your credentials for actually accessing those the cloud you just set up. And so you might be wondering here, okay, so you just showed us these 4 commands. What does it actually set up? Well, it sets up this very complicated thing for you. So basically, what is exactly like Sunbeam? It's a cloud-native OpenStack that's managed by Kubernetes. So effectively what you can do is that you can take OpenStack, you can kind of split it into 2 planes. The first part is you have kind of the cloud control, so that hosts the OpenStack services that are kind of responsible for actually controlling OpenStack. So for example, you could say you have like Keystone, which is responsible for authentication within the cloud. You'll have Glance, which is kind of responsible for actually like serving up the different images that you'll request. And then you have like Nucciarone, which is for configuring the network of your OpenStack cluster. You'll have like the Nova controller, which actually kind of manages the virtual machines that you'll provision. And then you'll have like RabbitMQ for actually exchanging messages between the services. And then you'll get kind of more to the machine plane, which is the cloud data plane, which then kind of has the more on-the-metal services. So for example, you'll have the Nova compute instances. So those will be the virtual machines that you'll actually like run workloads in. And then you'll also have like Oven Chassis or Open vSwitch, which manages the networking for those virtual machines. And then you'll need kind of the storage for those virtual machines, which is provided by Microsoft. And then here, for the cloud management and governance, that's just basically how you actually interact with and drive the cloud. So you'll have OpenStack CLI command for actually like interfacing with it, and then you'll have Juju for actually managing the different services. And so now you'll kind of wonder, like, how do Charmed HPC and OpenStack Sunbeam go together? So I've kind of presented Charmed HPC as its own thing, and then kind of OpenStack as its own thing. So now how do you actually bridge the two together? And so the way that I look at it is that Sunbeam is kind of basically a substrate for Charmed HPC. So you'll basically have Sunbeam underneath Charmed HPC, and then what Sunbeam provides to Charmed HPC is kind of the compute instances, the networking, and the storage capabilities. And then effectively then, it doesn't really show up on the contrast of the projector, so I'll use a darker gray in the future. But what should be symbolized here is a little very faintly gray-white line, or a gray line, that shows kind of the degree of separation between Sunbeam and Charmed HPC. So you'll probably be wondering, like, okay, how do we actually, manage, Charmed HPC? How do we actually get it onto Sunbeam? And so this kind of goes back into Alistair's talk if you were here earlier, but open source applications, so obviously you have like, things like Slurm, Grafana, all that stuff that comes together, but where's the code that actually like operates those services, what actually brings them together and actually makes it such that they can work? And so for that, we have Juju. And the great thing about Juju is that it can basically work with any application. It can scale that application however it needs to be. It can put that application whatever platform it needs to be on, and it can basically put it on whatever cloud you need it to be on as well. And so if you're kind of wondering, like, okay, obviously that's a lot of promises that it's going ahead and making here. How does it actually go ahead and do that? Well, it uses charms. And so I might not try to make it sound as black magic as usual, because that's what Juju means in South African language. But the idea is that effectively what a charm is that it's operations as code. So you can look at it here like, okay, so you have your application. So for example, you could look at it and say like, oh, this is what, Slurm, or you could say this is Grafana, or this is NFS, this is SAFFS, and effectively like you have all these different things that you need to be able to do with it. So like, okay, you need secrets management. You need to be able to kind of control access to that SAFFS share, or you might be exchanging like the, say, like authentication token that the Slurm daemons use to basically trust each other. You'll also have kind of the observability bits, like how do we actually set up the metrics collection? You'll think of patching, like, okay, how do we actually apply updates? And then, also for like upgrades and logging and auditing, just kind of general software lifecycle stuff that while, you might not think of when you're actually deploying and setting up the system, these are very real things that you need to consider as you're trying to sustain a system for the long term. And so the great thing about charms that we can make for our HPC system is that they are very flexible. So basically you can have very composable architecture. So while you could look at how I actually set up, say like Charmed HPC or OpenStack Sunbeam, the nice thing is that you're not necessarily stuck to that way of thinking. It's like charms, as long as they have the proper integrations, can kind of be composed in different ways. And so for example, you could say like, oh, on AWS, I want to set up Kubernetes. I want to have, on that Kubernetes, a Postgres, basically integrated with like Apache Kafka with Prometheus, or you can also then say like, oh, I want more of a bare metal implementation where on top of that bare metal, I'm deploying OpenStack, and then on top of that OpenStack, I then have Kubernetes as well. Or you can then also say like, okay, I want to use a different cloud like Microsoft Azure, or I just want to have straightforward Kubernetes. And so then you might be wondering like, okay, so we obviously have this flexibility and composability. How do we actually go about putting them together? And so typically for that, what we'll go ahead is that you can use either Terraform or OpenTofu, open source. So, Tofu's my guy. But effectively, what you can use is, just declare your HPC infrastructure as code, and basically you can create these plans that basically say like, okay, how do you actually wire together Slurm and all its daemons? How do you wire Slurm with like MySQL? How do you wire it up with InfluxDB and all that? And so effectively, what these dotted lines represent here is kind of the integrations that exist between all the different services and how they're actually able to exchange data back and forth to go ahead and configure themselves. And so with that, if you found what we talked about today interesting, I do have this QR code here. What it'll do is it'll actually go take you to our documentation for Charmed HPC. So we are still a relatively new project within Canonical. And so, one thing that we've been really trying to focus on is actually building out our documentation so that more folks are actually able to use this stuff, because while I can come and give presentations and stand in front of you and wave my hands and say, oh, this is how everything goes together, oh, it's so great. Really what we're interested in is also actually gathering that feedback where it's like, hey, I'm not really an HPC user, but I want to learn how to use HPC. I went through your how-tos and I found this to be challenging. That's the kind of feedback that we want to hear, because that's how we're able to actually make our product better and all of that. So also, if you're scanning QR codes isn't necessarily your thing, I'll be at the booth throughout the weekend. So if you want to come up and talk, or maybe even get like a live demo, be more than happy to do that. So yeah, no, that's pretty good. And then the other thing is that if you are interested in kind of what we're doing in the high-performance computing space on Ubuntu, we actually do have a pretty active community. We meet once a week on Wednesdays, and we also do actually maintain a public presence on Matrix as well. So if you ever have an HPC question related to Ubuntu, we'll talk about other distros as well if we really need to. Be sure to jump in. And then, yeah, that's pretty much it. Thank you for coming to my talk. And yeah, any questions? And if you're interested in keeping the conversation going, feel free to scan the QR code. And thank you for coming.
Thank you, Jason. Do we have questions? All that high performance computing you've been doing at home. No, come on. Okay. All right,
Yeah,
we
not
have a little
exactly
break.
something you do in your garage, but we might be able to change that one day.
Well, I'm tempted. When I see your demo, I'm like, I'm going to put some computers together just to have some fun. But yeah. The suggestion is he's going to make a question happen.
Yeah.
All right, here we go.
Is the ARM processor supported?
Yeah. So we will be supporting ARM. That is something we're looking at. So obviously it's kind of fun because, when I develop, this is actually my work computer right here. So when I build the HPC systems and actually test it, and yes, you can have the hat. We build for x86 currently, but we do kind of have the policy of like, okay, ARM and RISC-V are realities, like we can't just ignore it. I mean, it's like you look at what's going on in China right now where there's a lot of interest being put into RISC-V, and a lot of folks are also interested in ARM since it allows, I guess you could say the public clouds to be a little bit more self-determined in how their architecture is actually put together because they basically don't have to buy things from Intel. Instead, they can license ARM from ARM and then build their own chips. And so it is something we are going to support. I think, right now it's like what we've been focused on, and now we're moving on from is that we were, the table stakes, like, okay, how can we actually put the cluster together and make sure it works and provide a good experience? And so now what we're doing is actually looking at kind of these more expanded use cases where it's like, okay, people want to use ARM, how can we make sure that, you can take Charmed HPC, you can deploy it on x86, you can deploy it on ARM without needing much or any manual intervention from the user. It's like they could honestly have no idea. All they have to do is just pass a string that says, oh, I want to use ARM instead of x86.
Any other questions? Well, then, thank you. Thank you, Jason.
All right,
We'll take
thank
a
you,
little
folks.